Bismillahirrahmanirrahim. Let's start the new chapter in this heat and mass transfer course. We are now going to start chapter number 7 of our book, which is Heat and Mass Transfer by Incorpore and Dewitt. And these are some of the major topics that we will be going over. We will start with the empirical method of finding out the convective heat transfer coefficient. In fact, convection heat transfer coefficient is majorly about, or a large portion of the matter that we would be covering in our course deals with finding out the convection heat transfer coefficient H. The reason is that H is not a materials property, and therefore H would vary upon different parameters which we have discussed previously. So it would depend upon the temperatures of the surface and the fluid, the conductivity of the fluid, the velocity of the fluid, the specific heats, and others as well. So therefore, a major problem that we usually come across in convection is to find out the convection coefficient. So over here we would be starting with the empirical method of finding out the convection coefficient, and then we will discuss the flat plate in parallel flow, in which we will discuss several cases such as the isothermal plate case and constant heat flux case. So in one scenario we would have temperature as constant, and in the other one we would have the constant heat flux. We will discuss a specific type of the flow in which is called unheated starting length, in which the heat transfer would not start right from the beginning of the plate. Rather, heat transfer will start from after a certain length of the plate has been passed. And then we will discuss the flow over the cylinder and the sphere, and the corresponding convection heat transfer for the cross flow over cylinders and in case of sphere as well. Chapter 7 in fact mainly deals about a lot of Nusselt number expressions. So in this chapter we have a table at the end of this book which we would be using very frequently, and that chapter and that list has got various expressions of Nusselt number. So we would be using one of those expressions of Nusselt number to calculate Nusselt number, and ultimately that Nusselt number will be used to find out the value of H, because we have seen in previous chapter that Nusselt number is HL over K. Or if it is the cylinder, so then we will write it as HD over K, where D would be the dia. So those expressions of Nusselt number vary with the conditions, means it will depend whether the flow is taking place over a flat plate or cylinder or sphere, and it will also vary with the type of the flow, means whether the flow is laminar and turbulent. So there are a lot of cases that are given in that particular table that I am talking about, and we would be referring to those cases, or to we would be referring to some of those cases very frequently, which we usually come across frequently. So we would be coming across expressions of Nusselt number, and we would be using those expressions of Nusselt number to find out the Nusselt number, and then we will equate that value as to HL over K or HD over K to find out the value of H. So this is what we would be doing most of the times. Chapter 7 in fact deals with the force flow, and not the free convection. So primary objective in a lot of cases is to determine the convection coefficient. This is what I was mentioning in the last page, that our problem is to find out H for different flow geometries, of course. for different flow geometries and for different flow conditions. So we would be obtaining specific forms of the functions that represent those coefficients. So we would be using those expressions of Nusselt number that are listed at the end of the table to find out the value of H. And we would be starting with the experimental or the empirical approach to find out the convective heat transfer coefficient, in which, of course, since it is experimental, so we would be requiring some equipment with the help of which we could measure some of the parameters, and then we would be finding out the unknown means H. So we would be coming on to that in the next slide. The theoretical approach. So over here it says that the experimental or empirical approach involves performing heat or mass transfer measurements. So we would be having measurements of Q and of temperature, and area, of course, would be a known quantity under controlled laboratory conditions, and correlating the data in terms of appropriate dimensionless parameters like Reynolds number, Nusselt number, and others, Prandtl number. The theoretical approach involves solving the boundary layer equations for a particular geometry. So there is another approach which is the theoretical approach, and it involves solving the boundary layer equations to get the expression of Nusselt number for a specific set of conditions. So let's start with empirical method. Over here we can see that there is a plate, and over the plate the fluid is flowing with free stream velocity u infinity and t infinity, and then there is a heater which heats up this surface, this plate. So electrical current will pass through this resistor and the plate will get heated up. So the temperature of the plate can be measured very easily using some thermocouple or thermistor or any other type of device. Similarly, the temperature of the fluid can also be measured in the same manner. So out of in this equation we would be having the values of Ts and T infinity. Area would certainly be a known quantity, area of this surface through which the convection heat transfer would be taking place, and then Q can be evaluated using IV, means it would be the product of the voltage difference and the current that would pass through the resistor, because that would be the heat that would be supplied to the plate. So then using Q is equal to HA delta T, since we know the rest of the parameters except H, we would be able to determine the value of H. So this is the experimental setup for measuring the average convection heat transfer coefficient, which we call H bar. Remember, in the last chapter we were discussing two types. One was the local convective heat transfer coefficient, and the other one was the averaged convection heat transfer coefficient. In those cases where we would be referring to the expressions of Nusselt number to find out to calculate the Nusselt number, and then equating that Nusselt number to HL over K or HD over K in order to find out the value of H. So the Nusselt number would be of this form. Means we would be having a coefficient C, and then there would be Reynolds number and Prandtl number in that expression of Nusselt number, and Reynolds number would be having some exponent and Prandtl number would also be having some exponent, and of course those value of C, M and N would vary with the surface geometry and the type of the flow, as I was discussing a little earlier. Okay, moving onwards, we will now start the discussion on the flow over a flat plate, and we would be discussing expressions for Nusselt number and some other parameters. Over here we have this hydrodynamic solution. Hydrodynamic means related to velocity, and over here we have got this heat transfer solution, means related to temperature, of course. So as we had seen in the previous chapter, number 6, Introduction to Convection, that while solving the functional forms of the solution towards the end, the portion which was related to, or the parameters that were related to hydrodynamic solution were the coefficient of friction related to velocity, and the one which was related to heat transfer was the Nusselt number. So we are looking at the same parameters over here. In the hydrodynamic portion, we have the coefficient of velocity and delta, which is the thickness of the velocity boundary layer, and over here we have got Nusselt number, which was a ratio of the heat transfer to convection, heat transfer by convection to heat transfer by conduction. Right. So over here we have got the heat transfer related parameters and expressions. This expression, which says that delta is 5x over Reynolds number. In fact, this equation can be used to find out delta, where delta represents the thickness of the velocity boundary layer at any x. So that would be equal to 5x. That is equal to 5x over root of Reynolds number. In fact, there was a scientist by the name of Blasius. He had first solved the momentum equation way back in early 1900s. I think it was 1908. So what Blasius had done, he was a German scientist, or so what he did was that he plotted a velocity profile u by u infinity. So it was a non-dimensional velocity profile. So he took that velocity profile u by u infinity, and he plotted it against another non-dimensional distance, y by delta. So both of the parameters were non-dimensional, u by u infinity and y by delta, and of course all those things have their usual meanings. So he then had developed a sort of a table wherein he had listed various values. So there is a derivation behind this expression, which is delta is equal to 5x over Reynolds number. But summarizing the whole discussion, it was due to the solution by Henry Blasius, which ended up in this particular equation, with the help of which we can determine the thickness of the boundary layer at any x, at any location. Kindly note that this particular page that we are discussing is related to the laminar flow. Is related to the laminar flow over the entire plate. So in fact there may be three sort of conditions. It may be laminar flow over the entire plate, or it may be turbulent flow over the entire plate, or it may be mixed flow over the entire plate, right? So right now we are discussing the expressions where the flow is considered to be laminar over the entire plate, over the whole plate. So this is the expression using which we can determine the thickness of the boundary layer at any particular location. X is any particular location along the length of the plate, and Reynolds number X means Reynolds number at that particular location, right? Because Reynolds number would have different values depending upon where we are on the plate. Similarly, the coefficient of friction and you can see over here it says CFX, right? So CFX means CF, coefficient of friction at a particular x. So you may also call it local friction coefficient, right? So again, we are discussing two types of parameters over here. One would be the local and the other one would be the averaged one. Just like we had local convection coefficient and averaged convection coefficient over the entire plate. So similarly, we would have a local other parameters as well, and averaged other parameters as well. So coefficient of friction is a ratio of tau to half rho uv square, or v or u infinity, free stream velocity. This is something that we had taken a look at the start of chapter number 6. So upon putting the things and going through the derivation, we will get it as 0.664 Reynolds number raised to the power minus half, or 0.664 upon root of Reynolds number. Now coming to the heat transfer portion, this is the expression for Nusselt number, where Nusselt number is HL over K if it is flat plate, or HD over K if it is flow through a pipe. But over here we are calling it, we have X in the suffix of Nusselt number. We have X in the suffix of Nusselt number. So we are talking about the local Nusselt number. So instead of having H or H bar, we are writing HX. So if it is a local Nusselt number, so it would be local convection coefficient times X, whatever X we are at. For example, if we are halfway the length of the plate, so X would then be L by 2, right? Over K. K would of course be the thermal conductivity of the fluid. And we had seen that how we ended up getting HL over K in the previous chapter's material, where we had divided the heat transferred via convection Q is equal to HA delta T by the heat transfer via conduction Ka delta T over delta X, and we had ended getting HL over K as the expression of Nusselt number. So this expression of Nusselt number, when solved, would give us this expression, 0.332 Reynolds raised to the power half Prandtl raised to the power 1/3. And another expression worth looking at is that delta over delta T is approximately Prandtl number raised to the power 1/3. Kindly note that over here it is Nusselt number X. So this expression for Nusselt number is, in fact, this expression for Nusselt number will be used if the flow is taking place over the flat plate, and if the flow is laminar over the entire plate. And this expression will give us the value of the local Nusselt number, right? Now moving onwards, the average boundary layer parameters, which are equations 729 and 730 of our book. So when we say average, so we have this bar over this parameter CF, and similarly we have a bar over Nusselt number. So some people write it in this way, or some people just write Nusselt number and then put a bar. So whenever we see a bar, we should understand that we are discussing average Nusselt number over the entire plate. And if we see Nusselt number written in this form, Nusselt X, so we should understand that we are dealing with, or we are discussing local Nusselt number. So the average coefficient of friction would be 1.328 Reynolds to the power minus half, and an average Nusselt number would be 0.664 Reynolds half Prandtl 1/3. Now if you see, there is a particular relation between those two expressions of coefficient of friction, between those two expressions for coefficient of friction and those two expressions for Nusselt number. And you would have figured out by now that the average expression for Nusselt number is in fact twice the the expression for local Nusselt number. but it is only for the laminar flow over the flat plate. There are of course derivations behind all those expressions. So if we want to find out the local Nusselt number at any point, we would be using 0.332 Reynolds half Prandtl one third, and if we are to find out the average Nusselt number, we can use 0.664 Reynolds half Prandtl one third. Similarly, a Nusselt number can also over here it says for laminar flow over an isothermal plate. So right now we are dealing with isothermal plate expressions. We will be as I had explained on the second slide, that we would be discussing two types, isothermal case number one, and constant heat flux case, constant temperature case and constant heat flux case. So right now we have started with the isothermal case. So various scientists have tried to work out expressions of Nusselt number using various methods, and they more or less give the same answer, and some of them are applicable for certain ranges of Prandtl number, and some other are applicable for other ranges of Prandtl number. So over here we would be looking at only those expressions that are more commonly used, that are more commonly used. However, there you will find out some other expressions of Nusselt number besides the two that are written over here. So over here the next one that we are discussing is for laminar flow. For laminar flow, when the flow would be laminar over the entire plate, right? Over an isothermal plate, a single correlation equation which applies for all Prandtl number, which was given by Churchill and Ozo, is given in this form. Right? And again, it is for local Nusselt number, and average Nusselt number can be evaluated by multiplying the Nusselt number by multiplying the local Nusselt number by 2. So, but these are the ones 0.332 Reynolds half Prandtl one third and 0.664 Reynolds half Prandtl one third are the ones that we would be using more often. These are the ones that we would be using more often. So we would be calculating Reynolds number and Prandtl number, right? So with the help of this expression or this expression, we will be able to find out Nusselt number, and once we find out Nusselt number, we will then equate to HL over K to find out the value of H, because H is not required in Reynolds number or Prandtl number, right? So this is how we would be solving the problems. This is how we would be this would be our approach for finding out the value of the convective heat transfer coefficient, be it a local convective heat transfer coefficient or averaged convection heat transfer coefficient. A very unique expression for Nusselt number for liquid metals is given as 0.564 Peclet number raised to the power half. See, what happens with liquid metals is that they have very high thermal conductivity, right? Because it is metal, so they have got very high thermal conductivity. And as we were discussing in the previous chapter, that for liquid metals Prandtl number was very small, was very small, right? So they were of the order of 0.0 something, as is mentioned over here. So over here another dimensionless number, Peclet number, is defined, which is a simple product of Reynolds and Prandtl. So it is in fact written as 0.5664 Reynolds half Prandtl half, and that the product of Reynolds and Prandtl has been written as Peclet number. But this can only be used if we have got very extremely low Prandtl number, which corresponds to liquid metals only. And if you recall, Prandtl number of air was about of the order of 0.7, and then the Prandtl number of oils and other viscous fluids were having higher values. Now moving on to the turbulent flow over isothermal plate. So right now we are still considering the isothermal plate, means that the whole plate is considered to be at the same temperature of Ts. However, now we are considering turbulent flow over the entire plate. So some people have tried to solve the equations, and some people have tried to find out the things empirically. So over here we would be discussing the results. First of all, delta is 0.37x over fifth root of Reynolds number if the flow is entirely turbulent over the isothermal plate. However, as we had seen on the previous page, that this delta, which is the thickness of the hydrodynamic boundary layer, was 5x over root of Reynolds number. Over here it is 0.37x over fifth root of Reynolds number. And then CFX means the local coefficient of friction if the flow is entirely turbulent over the isothermal plate is given as 0.0592 Reynolds number to the power minus half, and the CFX bar means the averaged friction coefficient for if the flow is turbulent over the isothermal plate is given as 0.074 Reynolds number raised to the power minus 1.5. Again, you can see that over here the averaged values are not the twice of the local values which was there. So it was the local if the average values were equal to twice of the local values only if the flow is entirely turbulent over an isothermal plate, otherwise it won't hold good. And over here you can see as is mentioned over here that the turbulent boundary layer growth is much rapid. How it is much rapid? Because we can see that delta is x, and then over here we have Reynolds number raised to the power minus 1.5, and Reynolds number is given as would have x in the numerator, right? So it would be rho Vd over mu, or rho V L over mu, or rho V x over mu. So we would have x raised to the power minus 1.5 over here, minus 1 by 5 over here, and we have x in over here as well. So if the base is the same and multiplication is taking place, then the powers would get added up. So it would be x to the power 1 minus 1 by 5. So therefore it would be x to the power 4 by 5, right? X to the power 4 by 5. Whereas in case of laminar flow it was only x to the power half. How it was x to the power half? Because over here we have got this x, and over here we have got this x to the power 1 by 2. So 1 minus 1 by 2 would be half, means 0.5. And over here it is 4 by 5 means 0.8. So therefore turbulent boundary layer growth is more rapid as compared to the laminar boundary layer growth. Coming on to the heat transfer portion, the Nusselt number expression, again it would be Hx over K, and that is if we solve it we get this expression as 0.0296 Reynolds to the power 4 by 5 Prandtl to the power 1/3. And the average Nusselt number is not simply the twice, rather it is 0.037 Reynolds to the power 4 by 5 and Prandtl to the power 1 by 3. So those expressions that are mentioned over here, those hold good only when the flow is turbulent over the entire plate. When the flow is turbulent over the entire isothermal plate, or if the laminar region of the plate is very small, as compared to the turbulent flow region, right? So there may be two cases. Number one, either the flow is turbulent over the entire plate, or it is also a possibility that the laminar flow is very takes place for a very small distance. So the laminar flow region of the plate is very small as compared to the turbulent flow region. So therefore the critical we may say that x critical is much less than L. Means x critical means the value of x where this transition from laminar to turbulent flow takes place. So in this case, if this is the condition 2 that we have been discussing, so therefore x critical would take place at the start of the plate. So therefore x critical would be much less than L. So it may be any of the two cases. Now the mixed boundary layer conditions means we had started with the laminar flow over the isothermal plate, and then on the previous page we discussed the turbulent flow over the entire plate, and now we are going to discuss the mixed boundary layer conditions. So in the mixed boundary layer conditions, let's take a look at the first para. What does it say? It's very easy discussion over here. It says for laminar flow over the entire plate, for laminar flow, right? For laminar flow over the entire plate, over the whole plate, equation 729 and 730 may be used to compute the average coefficients. So we had seen 729 and 730 over here, which were the expressions for coefficient of friction and Nusselt number, average values of the coefficient of friction and Nusselt number for the laminar flow over the entire isothermal plate. Now then it says that moreover, if the transition occurs towards the rear of the plate, means if x critical by L ranges in this lies in this range 0.95 to 1, means if x critical is 0.95 L, or if it is near L, right? So it means that if the transition occurs towards the end of the plate, so for approximately 95 or 96% of the total length of the plate, the flow was entirely laminar, and then transition occurred towards the very end of the plate. Even then those equations 729 and 730 may be used to compute the average coefficients to a reasonable approximation. So because for 95 or 96 or 97% of the time the flow was completely laminar. So for 2 or 3 or 4% of the time, even if it becomes turbulent, so we will consider that flow as laminar, and we can use those expressions and they will give reasonably good values. However, if the transition occurs sufficiently upstream of the trailing edge, trailing edge would be the edge where the plate would end, means if x critical by L is less than 0.95, right? So if the transition is taking place before 95%, so then the plate would be considered as having mixed flow, right? So there would be laminar flow over there as well, and turbulent flow over there as well. So in such cases, the average coefficient over the entire plate, means for example HL bar, right? Average coefficient over the entire plate is determined by performing integration over two parts, 0 to x critical and then from x critical to L. So you can see over here, what does it say? 0 to x of hx dx by L. So if you recall, what was integral of hx dx by L? It was equal to the average value of the convection coefficient. But over here what we are doing is that we have divided this whole L, we have divided this whole length of the plate into two parts, and of course the one corresponds to laminar and the other one corresponds to turbulent. So we have from from 0 to x critical have considered the flow as laminar, and from x critical onwards till the end of the plate, we have considered the flow as turbulent. Where it is assumed, kindly take a look at the last sentence, where it is assumed that the transition occurs abruptly at x equal to xc, because we have not considered the transition period over here. So what we are saying is that the flow would abruptly become turbulent from laminar flow at x critical, at x is equal to x critical. So this is a small assumption behind this thing. Now for the mixed boundary layer conditions, these are the expressions for Nusselt number that you can get if you perform those integrals that were being shown on the previous page. And over here, this is what we were talking about, that H would during the laminar flow region, H would continuously decline. This is what we had explained in the previous chapter. And of course, during the turbulent flow, H would also decline. And at x critical, we will assume that the flow would abruptly change from laminar to turbulent. So we are not considering that transition period over here. The expression for average Nusselt number is given as 0.037 Reynolds to the power 4 by 5 minus A times Prandtl number 1/3, where A can be calculated using this expression. However, if you calculate the things, you will get the value of A as 871. I had done it and I had found it as 871. So you may use 0.037 Reynolds 4 by 5 minus 871 times Prandtl number 1/3. So you would have seen that, and over here there are ranges of Prandtl number as well, 0.6 to 60, and Reynolds number ranges from critical value to 10 to the power 8. I suppose that you would know the value of the critical Reynolds number. It is 5 exponent 5 for the flow over a flat plate. So you would have realized by now that all those expressions of Nusselt number are in terms of Reynolds number and Prandtl number. This is what we were discussing earlier on the empirical method slide, where Nusselt number was written as some coefficient C times Reynolds number to the power m and Prandtl number to the power n. So almost all the equations of Nusselt number that we will come across would be in terms of Reynolds number and Prandtl number. The coefficients would get changed, the terms would get added up, right? For example, over here 871 got added up. But the original form would remain the same, right? It would be in terms of Reynolds number and Prandtl number. Okay, let's go over this small topic of unheated starting length. In this particular topic, as you can see that if you see over here, the thermal modular does not start from the start of the plate, from the beginning of the plate. Rather, it starts from a certain point. After a certain distance xi or zeta, whatever you like to call it, is elapsed. So it will take after this particular distance has gone by. Let's go over the equations first, and then we will discuss how can we have such situations. So over here you can see that the velocity modular would start developing right from the start, because the changes in velocity would be experienced right from the start of the plate. But for a certain length, for this certain length, Ts is T infinity. and if Ts is T infinity, of course no heat transfer will take place between the plate and the fluid. So therefore the thermal bonding layer will not develop if the heat transfer is not taking place, of course. So as long as Ts is the same as T infinity, the thermal bonding layer will not be developed. However, if Ts is different from T infinity, only then the thermal bonding layer will start getting developed. Now over here, so in this particular region of this length zeta, Q would of course be 0 for the reason that I have just mentioned. Now for the laminar flow, we have this expression which says Nusselt number, and it is the local Nusselt number, is a ratio of Nusselt number at zeta is equal to 0 over 1 minus zeta over x raised to the power 3 by 4 whole thing raised to the power 1 by 3. Of course you do not need to remember those expressions by heart, right? Of course you would have those expressions available. All you need to do is to be good at selecting the right equation. This is what you need to be good at. For example, what I have seen various times is that students select the expression for Nusselt number wrongly. And how do they do that? For example, they either assume or wrongly calculate that the flow is turbulent, and then they choose the wrong expression of Nusselt number. However, the flow was laminar, right? Or it may be unheated starting length in some cases, or there may be other instances where you may end up selecting a wrong expression for Nusselt number. Right? This is what you should be very careful at. You, from that list of the expression of Nusselt number, you should be able to select the most appropriate expression of Nusselt number. Right? This is what you need to be very good at. You do not need to learn those expressions by heart, of course. So over here it says that Nusselt number is a ratio of the Nusselt number at zeta is equal to 0 over 1 minus this thing, right? So if zeta is 0, right? So what will happen is that in the denominator we would have 1, and Nusselt number would be the same as 0.332 Reynolds number half Prandtl number 1/3, right? Because this, where is this coming from? This is the expression for the local Nusselt number when the flow is laminar, right, over the entire plate. This is what we had seen 3 or 4 slides back. And for turbulent flow, Nusselt number, local Nusselt number would be given by this expression, where only the exponents in the power would get changed. Again, where local Nusselt number at zeta is equal to 0 would be 0.0296 Reynolds to the power 4 by 5 and Prandtl to the power 1 by 3. Now this numerator, which has got Nusselt number, local Nusselt number at zeta is equal to 0 for both laminar flow and for turbulent flow. So what is this thing, Nusselt number at zeta is equal to 0? In fact, if you talk about this quantity, let's go over the last one and then we will discuss then. Now for a plate of total length L with laminar or turbulent flow over the entire surface, Nusselt number is given as per this expression. Where P is equal to 2 for laminar flow and P is equal to would be considered as 8 for turbulent flow. Right? So now, for example, over here when it says Nusselt number, average Nusselt number at zeta is equal to 0, what does this mean? Of course, that is the average Nusselt number because it has got a bar on it. So it would be the average Nusselt number. It would be the average Nusselt number for the plate which would have a certain length equal to L. For example, even in here we can see that x is equal to L, so L is the total length of this plate. So for example, when we say Nusselt number, average Nusselt number at zeta is equal to 0, so it would mean the average Nusselt number, of course, for a plate which is having a length of L or whatever the length is, where the heating would start from the leading edge. Means heating will not start at this point, so only when the heating starts right from the beginning, so then zeta would become 0. Right? So what is zeta? Zeta is in fact the unheated length. Zeta is in fact the unheated length. So if zeta is equal to 0, it means that the unheated length is 0. And if unheated length is 0, therefore that would mean that the thermal boundary layer would start developing right from the beginning of the plate. So if zeta is equal to 0, that would no more be the case of unheated starting length. That would be the usual case that we were discussing in the previous 3 or 4 slides. Now the thing is that are there any examples of unstarted heating length? Well, of course, you should be able to find some if you Google the things or if you think over something. But there may be several. Cases where unstarted heating length would exist. For example, in the case of flat plate collector, right? In the case of flat plate collector, flat plate solar collector, I hope you would be aware of this thing. So we have a box, and inside a box we have got a black colored absorber plate. So when the air would start flowing, so a little amount at the beginning of will not will so when the fluid will flow over that plate, so in the beginning it will not get heated up. So therefore a flat plate collector may be considered as that of unheated starting length, or there may be a chip or some chip or some heat producing elements that are in an integrated circuit. Right, so the integrated circuit would start earlier, and the chip would come somewhere in the middle or at any other place. So when the air would start flowing over that IC, over that integrated chip, so it will only get heated up when it would flow over that heat producing element or that chip. Right, so that is also an example of unheated starting length, and you may find some others over the internet as well.